So let's continue this lecture with time scaling. So this is one of the time manipulation and operations that we are going to see. So in the last lecture we saw time shifting. Now we are going to see time scaling. So remember, we saw an example where we had an audio signal and then we shifted where it started and then we compressed it, expanded it, essentially speeding up or slowing down. So this is the operation that we are going to slightly see in more detail today. Basically what we are going to see is how to represent this using this mathematical model. So remember, whatever we are doing in this course is modeling whatever is happening in practice. So we are modeling this operation of slowing down or speeding up signals. It can be an audio signal or it can be a video signal. So we saw an example of the audio signal using the app Audacity. You can do the same thing with video also. You can speed up at the rate at which you are playing video, you can slow down. All these are all time scaling operations. So how do we represent this? Basically, if there is a signal x of t, the time variable, the independent variable, is scaled by some constant x a of t. Okay, so this is the scaled version, time scaled version. It can be either a sped up version or it can be a slowed down version. So when is it a sped up version? So if a is less than 1, that's the first one. Okay, so let's assume that for now, let us assume that a is positive. Okay, this is case 1. When a is less than 1. So what happens in this case? So let us take for an example, a is equal to 2. A is equal to 2. Then what happens to 2 times t? So in this case, the signal expands. That is, if we had a signal of this form, let us say we had a signal that something looked like this, for example. Okay, this is, let's say, minus 1, 0, 1, this is 1, this is t, this is x of t. Okay, now let's plot the scaled version of this, x of 2t. So if you want to plot the scaled version of this, scaled such that scaling factor is 2. So if we do this, well, in this case a is greater than 1. So okay, let's first say okay, a is 2, which is greater than 1 and positive. Okay, so what would be the time values corresponding to these points here? Right, at t is equal to minus half, we'll get x of 2 times minus half to be equal to x of minus 1, which is exactly this point, right? So we'll get that point to be shifted to minus half and 0 will remain as such, and then x of 1 will happen when t is equal to half. So similarly, this point will become half. Now let's see what happens when a is equal to half. In this case, a is less than 1 and still positive. So what happens to this signal? So let's see what happens in this case. So when t is equal to minus 2, then we have minus 2 divided by 2, which is x of minus 1. So the minus 1 point now moves to minus 2 and 0 still remains the same. And when t is equal to 2, 2 divided by 2 is 1. So this point moves to 2. So we have a signal which looks like this, it gets expanded. So that is what we say, that when a is greater than 1, or the absolute value of a is greater than 1, then we have the signal to be compressing. That's what we saw here. Signal gets compressed. And when it is greater than 1, we see compression, and when it is less than 1, we see expansion. But one thing to note here is, if you see in this graph, the 0 remains in place. So x of at, no matter what the value of a is, at t is equal to 0, at t is equal to 0, x of t equal to 0 is going to be equal to x of at, which will also be 0. So this compression and expansion operation is always going to happen about the line t is equal to 0. In other words, the compression and expansion is always centered around the y-axis. So this is simply because when you scale something, it expands about this t is equal to 0 point. It's going to expand or compress about the origin. So because of this reason, you can always fix the center point. The center point that is passing through the origin is always fixed. That point is never going to move because of the scaling operation. It will move only with the shifting operation. The origin will move only with the shifting operation, but not with the scaling operation. Okay. And if a is positive and it is less than 1, you get the signal to be expanding. If a is positive and greater than 1, you get the signal to compress. We saw in these examples. So this expansion or shifting or expansion or compression about the point t is equal to 0 or about the origin is what we refer to as anchoring. Okay. Now we saw the cases where a is positive. Now what if a is negative? Let's take this example itself and then see what happens when a is negative. So let us say here we want to see what happens when a is equal to minus 3. Okay. If a is minus 3 at t equals minus 1 by 3, what do we have? X of 8 times minus 1 by 3. This is equal to x of 1. So the point that was here starts appearing at t is equal to minus 1 by 3. And remember, 0 remains as such. And then when x of 3 is computed, you have x of minus 3 divided by x of 1 by 3. So basically here we try to compute t is equal to 1 by 3. Okay. Then this is x of minus 1, which is this point, right? So the entire signal flips. So this is what we refer to as time reversal. So whenever a is negative, then we have time reversal to be happening. Basically the signal flips about the point t equal to 0. It flips about the y-axis and it can expand or compress depending upon the absolute value of a. Once again, if a is negative and if a's value magnitude of a is less than 1, then we see that the signal gets reversed, time reversed or flipped, and then it expands. So magnitude of a is greater than 1 and it is negative, then it gets time reversed and it is compressed. Okay. Let's see some examples. As usual, we will see the standard signals and then we will understand what happens to these standard signals when we scale them in time. So the first signal is u of at. What is u of t? U of t is, if you remember, you plot t, u of at, let's say a is equal to 2. Okay. So this is now let us plot u of 2t. So what do you think happens here? So because a is greater than 1, it's going to get compressed. And remember, the compression or expansion is always going to happen about the point 0. So the 0 point comes as such. But then this signal extends from 0 to infinity. So it remains identical even when you plot u of 2t, because it's still the same. And let's see what happens when you try to plot u of minus t by 2. Okay. Now there is a negative sign in A, which means the signal is going to reverse or flip. So we have the signal to flip. Okay. And then the magnitude of A is less than 1, which means it will expand. But once again, in this case, A is, or the signal is going to extend from 0 to minus infinity. So the expansion or compression will not be visible when we plot it, because the signal is anyway extending to minus infinity. In all these cases, the magnitude does not change. Now let's see what happens for the ramp signal. This is 0, and at 1 we have 1. This is the ramp signal, and this is the rect. And the last one is cos. Now let us see what happens when we try to compute the ramp of 2t. Okay. What do you think happens here? So again, t here is multiplied with something which is positive and which has a magnitude which is greater than 1. So which means it's going to get compressed. So when t is equal to 1, you compute r of 2. R of 2 is 2. So then at this point, we get the function's value to be equal to 2. Remember, at the origin, it still remains the same. So 0 gets mapped to 0, but now 1 gets mapped to 2. That is t, for every value of t, you get multiplied with 2. So half gets mapped to 1, 1 gets mapped to 2, 2 gets mapped to 4, 3 gets mapped to 6, and so on. So the slope basically now increases. Okay, so here the slope, in this case the slope was 1, in this case the slope is 2. So the signal now gets compressed, as you can see here. So if we plot it in the same graph, then we'll see something like this. Let's say this is 1. So this will be x of t, and this will be this is r of 2t, and this is r of t. Okay. So as you can see, the signal gets compressed. Now what happens when a is minus half? We are trying to plot r of t by 2. So first thing we know is definitely that it is going to flip. So the signal is going to appear only on the left hand side and not on the right hand side. So 0 gets mapped to 0 as such. Now what happens when, let's say, t is minus half? When t is minus half, then we are trying to compute r of 1 by 2. So then at this point, we'll just have half. Okay. And when t is minus 2, we'll have r of minus 2 times minus 1 by 2, which is 1. So now this signal will appear like this. Okay, this is your time scaled ramp. Okay, it got time reversed and it got expanded. Now let's see what happens to the rectangular function. Okay, so once again we are trying to plot 2 times t, which means at t is equal to minus half, we'll have rect of minus 1. This point gets mapped to minus half, and this point gets mapped to plus half. Okay, and what happens to the cost function? So let's probably mark some points here. So let us say this is 1. So this will be 1 if omega is set to be 2 pi. Okay, sorry, it will be 1 if omega is pi by 2. Right? Yeah. So let's assume that omega is pi by 2. So at that point, the angular frequency is pi by 2. So now this is minus 1, and this point will be 2, this point will be 3, and this point will be 4. Okay. Similarly, this point will be minus 2, this point will be minus 3, and this point will be minus 4. Now let's see what happens to the cost value. So once again, the cost is going to now shrink. So it's going to appear like this. Now what is this 0 crossing? So we know that 0 gets mapped onto 0. So this point directly gets mapped here. And when will this point be mapped here? At t is equal to half, we'll have here pi by 2 times half times a, where a is 2. So that half gets cancelled. So we'll still have cos of pi by 2 when t is equal to half. So the point which was 1 here gets mapped at t is equal to, this is half. Okay, and this point which was at 2 gets mapped to 1, and so on. Okay, so similarly this is minus half, and this is minus 1. Now let's see what happens when something interesting happens for these two functions when a is negative. When a is negative, you still get the same shape here, right? But then the signal expands. Okay, so this is minus 2, this is plus 2. Okay, when t is equal to 2, you plug in at u of rect of minus t by 2 into the value of t is 2. So whatever you're computing at this point is rect of t divided by minus 2, which is t of rect of minus 1. So this point gets mapped here, and this point gets mapped here. So there is a flipping, but then the shape still remains the same. Okay, so this is because there is symmetry in this signal about the origin. So remember, what we are doing in shifting is always shifting about in scaling, what we are doing is always scaling about the origin. So what we are doing here is now symmetric about the origin. The signal itself is symmetric about the origin, and we are doing some operation which is about the origin. So here nothing changes in the shape, but of course it is now going to get expanded above the origin. Same thing happens even for the cosine function, because remember, cos of minus omega t is equal to cos of omega t. In other words, this is symmetric about the origin. So even by putting in minus t or putting in a value of a which is negative does not change the direction of the signal, meaning time reversal does not change the shape of the signal, but it can only get expanded or compressed. So in this case, it is going to get expanded. So you'll have something like this, and of course it's going to keep extending on both sides. So the 0 point will remain as such, and this point will be 2, and this one will be minus 2. Okay, so this is how we typically take time shifting operation, and then interpret that as an expansion or compression of a signal or time reversal. Now take an exercise, do an exercise, take this signal x of t here, and then try to plot x of 3t and x of minus t by 4, okay, and then see what happens. So this is the time scaling operation.